can zoom into their infinite detail, size them on YouTube and tattoo them onto our bodies. Personally, I got myself the animated version, which hurt a lot to get, but it wasn't as much pain as you're about to experience in this tutorial. We're going to be using some math, some coding, and some OSL shaders, which stands for overly complicated scripting language, to create this node which will let us control our fractal. So be warned, this is going to be a pretty complicated tutorial, so either learn the prerequisites or get ready to blindly copy some code. This isn't plagiarism, I swear. And when you're ready to devote your life to fractals, just grab a keyboard, grab some coding glasses, and grab the newest version of Blender so you too can spiral into madness in 3, 2, 1. So as you hopefully know, a plane is made of a bunch of points, each with their own xy coordinates, or with complex numbers that each have some value x plus iy. For example, this point represents 1 plus 2i, this point represents -2 minus 2i, and this point represents your skill in Blender, which is exactly 0 plus 0i. And with complex numbers, we can easily add them by adding the real and imaginary components, multiply them by doing this thing, which gives us this result, and measure their magnitude using the Pythagorean theorem, which gives us the distance from the origin. Now going back to fractals, we're going to be using this equation to generate them, where different c values make different fractals, and here's how it works. Basically, z is going to be the point on the plane we're currently looking at, which we then square, add, and get an output for, and we then take this, plug it back into the equation, and get a new output, and repeat this process over and over and over. And if at any point our magnitude becomes larger than some chosen threshold, we then stop this nonsense and assign our point a color, which represents how many iterations this took. So a point that took lots of iterations will be closer to white, a point that took less will be closer to black, and when we do this for all our points, we're going to get a final image that looks like this, this, or this. And hopefully you got that all down so we can hop into Blender and do our OSL programming in 3, 2, 1. So with Blender open, to racinate the default cube, replace it with a plane and switch over to cycles with OSL enabled so we can actually see our scripted materials. Now in the shading workspace, we're going to toggle over to rendered mode, create a new material for our plane, and swap the principled BSDF node for a script node, which you can think of as a container for all the code we made. And this of course means we need to put on our coding glasses because it's time to start scripting. And to do this, just open up the text editor with all formatting options, create a new text file with a custom name, and import this into our script node. We're now going to create a new shader called Fractal, add in 2 float inputs for the real and imaginary components of our C, and initialize both of these to 0. And this gives us 2 inputs we can now play around with, but we're still missing the points from our plane and the output color of our fractal. And to fix this, we're just going to add our points as a parameter called position, create a color output called fractal color set to 0, and refresh our node and hook it into the material output node. Finally, we need to program in our fractal equation, but before we do that, let's calm down, take a breath, and take a 3-second break to gather our thoughts. Okay, so we now need to add in our fractal equation, and to do that, just create some variables to store the points xy coordinates, add in a simple for loop with some large number of iterations, and update our components using the fractal equation, which can be decomposed into a set of real and imaginary equations. And notice that currently, after updating our real value, we're using this already overridden value to calculate our imaginary component, which is not what we want. Instead, we're going to store this in a temporary variable and use that for the imaginary component equation. Finally, add in an if statement to check if our current iterate has a magnitude larger than our threshold, and if so, set the output fractal color to be the current iteration over the total number of cycles. And CG Matter says it's okay to take off your coding glasses now because we're done scripting and have our completed fractal node. We can use the real and imaginary C sliders to control the type of fractal we get, add in some coordinates to move this around and zoom in, and send this through a color ramp node to control the color of our output. And there you go, another non-beginner friendly, beginner-friendly tutorial to study for months and months. I've been CG Matter, you've been you, bye-bye. So because you watched my amazing video, I already know you love fractals, myself, and learning valuable skills online, which means you're gonna love our sponsor for this video, Skillshare. And Skillshare is an online learning community with over 25,000 classes, including material like Blender, coding, and tons of other useful subjects. So, I hope you brought your helmet today because today I'm gonna make your brain fucking explode. I don't want you to get chunks everywhere. We should have this nice and contained. I'm gonna be showing you how to achieve stupidly, just absurdly complex results using very few nodes. Specifically, I'm gonna be showing you how to make fractals without looping, without coding, just your good old procedural nodes that we have control over. And I guess, with this intro, I have you hooked in. I guess we should just begin. So, specifically, I wanna make this kind of fractal, which has a name. I think it's called Sierpinski gasket, but it might be a different thing, and I might have just, maybe it's called a carpet, I have no idea. But it's this fractal that kind of takes the center square, being this black square, cuts it away, and then it kind of repeats that for these 8 neighbors, and then again and again and again, and you can see how this is like self-similar repeats, and we can zoom in here, and there's no coding done for this. In fact, what I did is I just created a single node group, being this one, copied it a bunch of times, and that's what makes the fractal. So if I get rid of all this, you can see really what the node group does is it just punches away the middle square. If you were to divide this into a 3x3 grid, it punches that out, and then I just kind of duplicate it, and every time it adds another iteration. So no, we can't control the number of iterations without putting in all these extra node groups, but it's not like you need that many. Like at this point, I can't even see the additional detail unless I zoom in. And one more thing before we begin, and I show you how to do this, since this is going to be a bit mathematically intense if you're not used to it, I just want to make sure that you're ready. I don't want you, you got to be prepared. Okay, so it's not that it's just punching away the center. There's actually more going on here, and these nodes here aren't doing any help. They're not helping you see it, so I'm just going to get rid of them. What's actually happening is I took my texture coordinates, punched out the middle one, just like I said, but then also copied it for the other tiles, which is what makes it self-referential. So Generated coordinates looks like this. We just made 8 of those and punched out the middle one so that when you duplicate it, it just makes more generated coordinates, and then we did a bit of a trick. So I guess I should show you how to do this. And by the way, I don't think I mentioned, by the way, we get more control than you might think. We can change where these squares are to kind of get a 3-dimensional effect. We can change the size of these squares to make different kinds of fractals. In fact, you can make an infinite number of fractals, and if people want, I'll show you the 3-dimensional version in a sequel, but you have to beg. I'm not doing it for free. I will do it for free, but you gotta beg. Let me just talk about how to do this without any more build-up. So, default Blender thing, I say use 2.82 or above since we're gonna be using the compare node, although if you're like a 2.7 hermit, I don't care. You figure it out yourself. 2.82 and above. So, cube, get rid of it. We're going to be using a plane. We're just going to be putting the fractal on the surface of the plane. Shading workspace, we're already halfway done. We've already done all our modeling. The rest of it is just nodes, so the tutorial's now wrapping up. We're going to go to the top view. Works with Eevee, works with cycles. I recommend Eevee because it's faster, and it's nice that it works with Eevee. So, new material. We're going to call this fractal for some mysterious reason, and then we're just going to be using our texture coordinates. So right now we have a plane and we're viewing our texture coordinates, which are, it's a 3-dimensional thing. It also has a z-axis, but we don't really care about that because it's infinitely thin. Maybe that's what I'm trying to say. So you could also use UV coordinates if you want that just eliminate the z component. And in fact, I think that's what I'm going to do. We'll save generated for the 3-dimensional version. I'm going to take this, I'm going to separate it by x, y, z. What does this do? It takes a 3-dimensional quantity. Again, UV is kind of 2-dimensional because z is constrained to 0. But we can extract the x-axis, or the x component, and the y component. Why does x go from black to white? Because this is the x-axis, left to right. It's 0 all the way here, and then it progresses to 1 as we get to the right. And then same thing with y, but up to down. So the origin is in the bottom left corner. Okay. So the idea, first of all, is we want to take our UV coordinates and, like I said, punch out the middle because that's what's happening with each iteration of the fractal. So how do we kind of isolate the middle? Well, since we have 2.82, it's actually very easy. We just use a math node. We set it to compare. So right now we're just dealing with the x component information, and then we're going to do the same thing for the y component. So we want to compare, and what this does, again, if you don't know, is it takes the first socket and the second socket, compares these two values. So we're saying x, compare this to 0.5 with a threshold of the epsilon. And let me just increase this so you can see what happens. It kind of makes this bar or stripe that goes vertically but expands horizontally. What's happening here is we're saying, Blender, make this white wherever x is within 0.22 distance of 0.5. If we make this threshold, this distance, this radius bigger, it's going to include more of it. If we make it close to 0, it's going to include less of it. If we change this 0.5, we're comparing to a different number, which looks like sliding. That's the idea. So we don't want it to just be any thickness. We want it to be exactly a third of the plane. And you might be thinking, okay, how do we know what it's supposed to be? Well, think about it like this. If you have a coordinate system where 0, 0 is right here, and you progress to 1 this way and this way, right now we only care about the x-axis, a third goes from 0 up to 0.33333, or a third, right? That's what we want. And this section goes from a third to 2/3. So how do we isolate it? Well, we say we're comparing to 0.5 in the middle. That's what we're comparing to. So we want to take 0.5, and then since we want this to be, kind of like a third across, or I guess, yeah, a third across, what we do is we subtract 1 divided by 3. Okay, so now what we're doing is we're saying 0.5 in the middle, and we want the overall thickness of this thing from left to right to be a third, meaning you just subtract a third. This is, so now, since we want this to be, kind of like a third across, or I guess, yeah, a third across, what we do is we subtract 1 divided by 3. Okay, so now what we're doing is we're saying 0.5 in the middle, and we want the overall thickness of this thing from left to right to be a third, meaning you just subtract a third. This is what happens. I think this is the same as 1 divided by 6. So there you go. Now you've isolated this area. And to do it with the y-axis, what do? You just duplicate it. You just kind of reuse the ideas from before, right? So y, plug this in here, and now we're taking y, comparing it to 0.5. Now we're treating this as kind of like a vertical thing, so kind of like rotated by 90 degrees, same thickness. So 1, 2. How do we kind of combine these ideas together to make it the square? Well, we want to say, Blender, where's the stripe going horizontally and vertically at the same time? Because that would kind of give us the intersection. This is the same thing as multiplication. whereas addition gives us an or. So multiplication gives us the square, addition gives us the cross. So we want multiplication. So far what have we done? We've isolated the center piece that we're eventually going to cut out. Okay? So how do we cut this out now that we've isolated this area? Well, what we need to do is we need to take our UV coordinates, this stuff, and subtract kind of this mask that we made. Pretty obvious. How do we do it? I'm going to use vector math because now we're not dealing with one-dimensional quantities with these math nodes, but in fact, three-dimensional vector quantities. That's why these have purple sockets. And again, it is two-dimensional UV coordinates. Forget about it. We're going to take UV coordinates, and your first instinct might be, okay, we want to subtract away whatever's white and black kind of do nothing. So you say, okay, subtract, and then you plug this in. And you say, okay, I've done it. I've kind of whereas addition gives us an or. So multiplication gives us the square, addition gives us the cross. So we want multiplication. So far what have we done? We've isolated the center piece that we're eventually going to cut out. Okay? So how do we cut this out now that we've isolated this area? Well, what we need to do is we need to take our UV coordinates, this stuff, and subtract kind of this mask that we made. Pretty obvious. How do we do it? I'm going to use vector math because now we're not dealing with one-dimensional quantities with these math nodes, but in fact, three-dimensional vector quantities. That's why these have purple sockets. And again, it is two-dimensional UV coordinates. Forget about it. We're going to take UV coordinates, and your first instinct might be, okay, we want to subtract away whatever's white and black kind of do nothing. So you say, okay, subtract, and then you plug this in. And you say, okay, I've done it. I've kind of cut out the middle chunk. Like, what's the issue? The issue with this is, and the reason it doesn't work, is this black area isn't actually set to 0. It looks like it is, but it's not. In fact, what's happening here is we have negative values, which makes sense since we subtracted some positive quantity. It's going to go to the negative region at least somewhere. And the fact is, Blender shows all of this is black. Anything below 0 is black, so we don't actually know if it's negative or just 0 everywhere, but believe me, it is. So instead, what we're going to do to fix this issue and actually get rid of it and set everything in the middle to 0 is instead of subtraction, we are going to use multiplication. So M for multiply, which kind of gives us the inverse right now, but the idea is here, right now, this is the black region, it's multiplying that area by 0, so the vector in those areas actually gets multiplied to 0 instead of going negative, just gets sent immediately to 0. Now, of course, we want the inverse of this since we want to isolate the middle, not do whatever's happening here. So to take the inverse, you could either use a invert node, which I wouldn't recommend because that's lame. Instead, just use more math nodes, set it to subtract 1 minus the quantity, inverts it, right? Boom, boom, boom. So you can see the inversion. The reason this works is we're saying 1 minus this area is 1 minus 1 is 0, so that's why it's black. And then this area, you have black, so you have 1 minus nothing, 0, so it's 1. It inverts it. That's what you have to know. Okay, cool. So you might think we're done with this node group and we can start copying it since we, I don't know why I'm trying to save, since we punched out the middle, but in fact, this is not the case. This is what happens when we try to do it. So I'm going to group it, Control G, and what I did before is I just duplicated it over and over, and you can see it's not actually doing anything. It's as if we're adding no information every time we add an iteration. The reason this is happening is because it's just mapping this image that we've made, this kind of UV texture almost, with the thing in the middle being black. We're taking this and just mapping it onto UV coordinates again and again and again, which isn't going to change anything. It's being mapped onto itself, right? What we need to do is we need to make tiles. So we need to make our 3x3 grid with this thing in the middle gone. So instead of feeding UV coordinates, into this multiplication, which is what gets rid of the center, we need to feed in tiles. So how do we make tiles? That's a good question. Here's a super simple trick to do it. Vector math, and I'm just going to view what we're doing here. What I'm going to do is right now we have our UV coordinates not manipulated at all because we're adding 0, and you could add some quantity to actually manipulate it. But right now we just have our UV coordinates. We're going to set this to scale, which is going to kind of, it's going to multiply in X, Y, and Z, but you can think of it as a strength or intensity. So you can kind of see what's happening here. We're going to use a strength of 3, so now instead of going from 0 to 1 on X and Y, it's going from 0 to 3, 0 to 3 because we've scaled it by 3, so now it's going 3 times further. And now what we want to do is, since we're going from 0 to 3, we just want to say, Blender, we have kind of too much going on in this square. Instead of going from 0 to 3, go from 0 to 1, 0 to 1, 0 to 1. So we're breaking it up into 3 components. To do this, add another vector math node, set this one to fraction, and let's view it. And it does exactly that. Now we have our 3x3 grid. Again, this works because here we have a 0 to 3 UV square, kind of. And what fraction does is it takes the numbers and gets rid of all the integers in the beginning. So 1.32 becomes 0.32. Pi, 3.14, blah, 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 becomes 0.14. So any number kind of gets mapped to 0 to 1. That's the idea. Okay, cool. So we have this, and then we want to do this multiplication. So we feed it in here. And now we have our tile, our 3x3 tile UV grid minus the thing in the center. And again, there's no reason you can't use generated coordinates, which would be useful if you're doing the three-dimensional version. It's just that this has a z component. I think right now it's averaged to 0.5. So if you wanted to, you could set this to subtract, not that, but z, subtract 0.25, I don't know. Subtract something and it will get rid of that blue. Whatever, we don't care about that right now. Okay, so now we have a completed node group, which I need to set to UV again. We have a completed node group. We can take all of this, I'm highlighting it, I'm hitting Control G for group, or you could right click group somewhere. Yeah, group, Control G. And now we have our UV coordinates feeding into this thing that takes UV coordinates and turns it into this. Well, if we take this and duplicate it, what's gonna happen? Well, it's gonna generate this. And now let's think about why this is the case, because this might seem like black magic. Think about what this node group does. What does it do? It takes in UV coordinates, it looks like this, and outputs this. Well, this thing has UV coordinates in each of these tiles, so it's going to perform the same thing just in a localized area again. So it's almost as if we're just taking this and shrinking it down 8 different times, but not in the middle. So it's just going to do the same thing. And now we still have UV stuff, it's just smaller. So we do it, whoops, not duplicate the plane, although that would be an interesting way to do it, but we do it again, and again, and again. Okay, so now we've actually kind of created this thing. There's like one technicality. We want this to be black and white. White wherever there isn't a square missing, black where there is that square missing. The trick I use for this, it's not exact, but it's fairly good, is what you do is you add in vector math at the very end of, in this case, 5 iterations. You could do more iterations. And what I'm going to do is I'm going to set this to length, which is going to take our vectors and output the, if you were to take a vector and compute the magnitude, the length of it, this is what it does. So a 0, 0, 0 vector, the 0 vector outputs a length of 0, a 1, 0, 0 vector outputs a length of 1, and then et cetera, et cetera. It uses the Pythagorean theorem as the idea. But the nice thing about length is this length is only going to be 0 exactly where there's these black squares, because those are the 0, 0, 0 vectors, so that has a length of 0, and at the very, very corner of each of these squares. So the origin of each of these is technically 0, 0, 0, but because we don't care about that one infinitesimal point, it's as if the entire thing's white. That's why this trick kind of works. Okay, so we view this, and you can see that right now it's almost doing what we want, but it's just outputting the length. So you can see again in these corners we have something that's getting really, really, really close to 0. What I'm going to do is I'm going to use a math node, and I'm going to say, take this and show me where it's greater than 0. So technically, it's going to give us white everywhere except for the very, very corners and these squares that we eliminated. So it looks perfect. There's no reason this doesn't work. And I guess one thing you already saw is we can make this a different number, so it's kind of making circles here. And this is a interesting effect in its own right, but whatever, I'm not going to be using this. So again, what did we do? We used the UV trick again and again and again. So now we have a very dense UV grid. We said, give me the length of this, and we said, tell me where that length is bigger than 0, which very, very precisely approximates what we need. And at this point, we can just pick the number of iterations. So 1, 2, 3, 4, etc. Okay, so you might think, this is pretty interesting. We didn't really need to make that many nodes to give us something that really looks like a fractal, even though it's not, it has a limited number of iterations. What can we do with this? Well, you can render this, but you can actually control much more, because these node groups aren't just duplicates, but they're instances of each other. So you can see next to each of these node groups, you see the number 5. If I add another, it should give us 6. And this is saying there's 6 instances, being like, it's more than a duplicate. If we manipulate one and manipulates the other, they're carbon copies. So since these are exactly the same, I can change instructions in the first one, and it will change instructions in all the others. What kinds of instructions would we want to change? Well, maybe this compare stuff, right? So we could change whatever this is. It drifts it on the x-axis. This drifts it on the y-axis. Again, if we were to unlink this, hit this, so now this is independent from these 5, which are now duplicates, so this is independent. This is only going to affect the first iteration being the first square, and it doesn't affect anything else, right? So we've kind of isolated it. If we were to do this again on like step 3, so now this is the one that's different from the others. This is only going to move like the 3rd largest square, so it looks like this. So you can just isolate component by component, but that's not what's interesting. The thing that makes fractals interesting is that they are self-similar, meaning the fractal itself exists within itself, just smaller. It's self-referential, right? So we want to have all these linked to each other. So I'm going to keep all these with their 6s or 7s or whatever. It computes really fast because we're not actually doing that much math. I'm going to go into one of these instances, and you could do any one of these because they're all duplicates of each other, carbon copies. And what I'm going to do is, instead of just manipulating one of these values, or we could do this one for the thickness of the square, is I'm going to use a value node to control 2 at the same time. Now you could do them independently from each other, which gives you rectangles instead of squares. But I do like keeping it as squares, so I'm going to use one value node here. And this is just going to be our kind of transition diagonally because it's controlling x and y. And then I'm going to make another value node, and this is going to be for our epsilon, the thickness, or the distance, or the threshold, whatever you want to call it. And this needs to be smaller than, I think, just 0.5 to actually see something. Yeah, there you go. And you can see this thing kind of generating, and then as these squares get really small, it goes to white. So we get this cool transition, but really every step along the way is a fractal in its own right that we can transition. So if I do this just right, I can't remember what the numbers are supposed to be, but that, like, the Legend of Zelda triangle thing, we can almost generate that. So you can kind of see how this looks the same, just kind of turned a bit. So let me go like this. Now you can kind of see the Triforce. It's kind of a wonked out version, but you know, it works, and we can make it look a bit different. So these fractals kind of exist within each other. And in some sense, a lot of these fractals that you know are all the same fractal. But yeah, we can do all this kind of stuff. It looks 3-dimensional, whatever. Like I said, you can make these independent from each other. You don't need to have like X and Y do the exact same thing if you don't want to. And in fact, you can generate many more fractals if you don't add that constraint. But yeah, there you go. I think I taught you how to make fractals pretty easily. And you could pick the number of iterations, and I think I already said all this. So we've reached the end of the show. I hope you enjoyed this tutorial. If you did, actually, before I say what I'm about to say, if you want the 3-dimensional version, so volumetrics fractals using this same idea, but a bit modified, let me know. I might make it, I might not. You know, you gotta really convince me. But if you enjoyed this free tutorial on YouTube, the best way to support this channel and get bonus content and keep me making those free tutorials is via Patreon. Patreon not only lets you be a patron and donate to this channel directly, but it gives you benefits. You get behind-the-scenes content, you get exclusive tutorials, Discord access. Trying to remember, exclusive blend files, so project files. Sometimes I upload those depending on the thing. Sometimes I upload fragments of videos, sometimes I upload them early, but you can find out about that on the Patreon. I appreciate anybody who is willing to do that. It really does help me, obviously. But you do get some stuff in return, so you can think of it as a transaction up to. Either way, I hope you enjoyed this free tutorial about fractals. I'm the best in the procedural game. Nobody can
So, meanwhile,
Oops.